Hello everyone, today we'll study linear independence. First of all, let me introduce what it is. Let V be a vector space, and let S be a set of vectors v1, v2 up to vn. Let S be a subset of V with at least two vectors. If no vectors in S can be written as a linear combination of the others, then S is called linearly independent set. Otherwise, S is called linearly dependent set. So, if no vectors in S can be written as a linear combination of the others, then S is called linearly independent set. However, if one of the vectors in S can be written as a linear combination of the others, then S is called linearly dependent set. Note, if S is a linearly independent set with at least two vectors, then the vectors in S, v1, v2, vn, the vectors in S, they are called linearly independent vectors. If S has at least two vectors and S is linearly independent set, then the vectors in S, they are called linearly independent vectors. Next, let's look at a simple theorem. Let V be a vector space, and let S be a subset of V with at least two vectors. If the zero vector is one of the vectors in S, if the zero vector is one of the vectors in S, then S is a linearly dependent set. If 0 is one of the vectors in S, then S is a linearly dependent set. How can we prove it? If 0 is one of the vectors in S, so we assume Vi is the zero vector. Assume Vi is the zero vector. Then Vi is the zero vector. Zero vector can be written as 0 times V1 plus 0 times V2 plus 0 times Vi minus 1. Vi is here, so skip Vi. Plus 0 times Vi plus 1 plus plus 0 times Vn. Here, I write Vi as a linear combination of V1, V2, Vn. Since Vi can be written as a linear combination of the other vectors, since Vi can be written as a linear combination of the other vectors, then if one of the vectors can be written as a linear combination of the other vectors, S is a linearly dependent set. Then S is a linearly dependent set. Let's complete the proof. So, if one of the vectors in S is 0, is the zero vector, then S must be a linearly dependent set. Next, let's consider a special case. Let S be a subset of V, which contains only one vector. Then, how can we define a linear independence for the set of only one vector? We know that the previous definition, it defined a linear independence for the set of at least two vectors. For the set of only one vector, in order to agree with this definition and this theorem, we define a linear independence for the set of only one vector in the following way. Let S be a set which contains only one vector V. If V is not 0, we define S to be a linearly independent set. If V is not 0, we define S to be a linear independent set. Because if S has only one element V, we cannot write V as a linear combination of the other vectors, because there are no other vectors. So, if V is not 0, we define S to be a linear independent set. If V is 0, in order to agree with this theorem here, this theorem says, if 0 is one of the vectors in S, then S is a linear independent set. In order to agree with this theorem here, if V is 0, we define S to be a linearly dependent set. So if S has only one vector, when this vector is not 0, we say S is a linearly independent set. When this vector is 0, we define S to be a linearly dependent set. So that's how we define linear independence for a set with only one vector. Another special case, let's consider empty set, a set of no vectors. Let S be an empty set. Then, if S is an empty set, you agree with this definition here that no vector in S can be noted as a linear combination of the others, because there are no other vectors. So, if S is an empty set, we define S to be a linearly independent set. If S is an empty set, we define S to be a linearly independent set. So, those are two special cases. If S has only one vector, if the vector is not 0, S is linearly independent. If the vector is 0, we define S to be linearly dependent set. And if S is an empty set, then S is always linearly independent, because no vector in empty set can be noted as a combination of the other vectors. So if S is an empty set, we define S to be a linearly independent set. Next, let me show you a theorem. Let V be a vector space. Let S be the set of V1, V2, Vn. Let S be a non-empty subset of V. Then S is linearly independent if and only if the only solution to the vector equation K1 V1 plus K2 V2 plus Kn Vn is 0. The only solution to this equation is K1 equals 0, K2 equals 0, and Kn equals 0. So S is linearly dependent if and only if the only solution to this vector equation is K1 equals 0, K2 equals 0, Kn equals 0. Let's prove it. This statement contains if and only if, so I must prove in both directions. First of all, from left to right, we assume S is linearly independent. We try to prove that the only solution to this vector equation is zeros. So, assume S is linearly independent. Assume S is linearly independent. We try to prove that the only solution to this vector equation is zeros. Now here let's consider two cases. Since S is not empty set, S may be one element, S may contain one element or at least two elements. There are two cases. S may contain only one element or at least two elements. Case 1. S contains only one element. S contains only one vector. Since S is a linear independent set and S contains only one vector, by this definition here, the vector in the independent set cannot be 0. If S contains only one vector and S is a linear independent set, then the vector in the set cannot be 0. So let S be the set of only one vector, V1. Then V1 cannot be 0. V1 cannot be the 0 vector. If S has only one vector, this vector equation can be written as K1 V1 equals 0. If S has only one vector, this vector equation can be written as K1 times V1 equals 0. Since V1 is not a 0 vector, then K must be 0. Then K1 must be 0. Therefore, the only solution to this vector equation is 0. So let's complete the proof for case 1. Let's complete the proof for case 1. The only solution to this vector equation is k1 to 0. Case 2. S contains at least 2 vectors. Case 2. S contains at least 2 vectors. So I let S equal to V1, V2, Vn. For the vector equation, set k1 v1 plus k2 v2 plus kn vn equal to 0. We try to show that all scalar k's are 0. All the scalar k's are 0. In order to show all k's are 0, we try to prove it by contradiction. So we assume one of the k is not 0. Assume ki is not 0. Assume one of the k is not 0. Then, this equation can be written as ki times vi equal to negative k1 v1 minus k2 v2 minus ki minus 1 vi minus 1. Ki is here, so next term will be ki plus 1 vi plus 1 plus minus the last term is kn vn. If ki is not 0, I isolate ki vi, move the rest to the right side. So I get ki vi equal to negative k1 v1 negative k2 v2 minus negative ki minus 1 vi minus 1. We skip ki. Ki is here. Next term is ki plus 1 vi plus 1 minus the last term kn vn. Since ki is not 0, I can divide both sides by ki. Since ki is not 0, I can divide both sides by ki. I get negative k1 over ki times v1 minus k2 over ki times v2 minus ki minus 1 over ki times vi minus 1 minus ki plus 1 over ki times vi plus 1 minus the last term is kn over ki over ki. Last one is kn over ki times vn. Here I write vi as a linear combination of the other vectors. Since vi can be written as a linear combination of the other vectors, since vi can be written as a linear combination of other vectors in S, then S is linearly dependent. That's a contradiction because we assume S is linearly independent. That's a contradiction. Since we find contradiction here, that means the assumption ki not equal to 0 must be wrong. Therefore, ki must be 0 for all I. equal to 1, 2, 3 up to n, which means k1 is 0, k2 is 0, and kn is 0. That complete the proof from left to right. Next, let's try to prove from right to left. Assume the only solution to the vector equation k1v1 plus k2v2 plus knvn is 0. Assume the only solution is k1 equals 0, k2 equals 0, and kn equals 0. We try to prove that S is linearly independent. So assume the only solutions to the vector equation k1v1 plus k2v2 plus knvn equal to 0. So the only solution is k1 equal to 0, k2 equal to 0, and kn equal to 0. We try to prove that S is linearly independent. So again, let's consider S in two cases. Let's consider S contains only one element or more than one element. Consider S in two cases. S may contain only one element or more than one element. Case 1. S contains only one vector. So let S be the set that contains only one vector v1. Then this vector equation is k1 v1 equal to 0. We try to prove that S is linearly independent. If S has only one vector, in order to show S is linearly independent, we must show that the vector in the set is not 0. So we try to prove that v1 is not 0. So here, try to prove by contradiction. Assume v1 is 0. Prove by contradiction. Assume v1 is 0. Assume v1 is a 0 vector. Let k1 equal to 1. Then k1 times v1 is 0. Which means k1 equal to 1 is a solution to this vector equation. Since k1 equal to 1 make this equation 0. k1 equal to 1 is a solution to this equation. That's a contradiction because we assume the only solution to this equation is k1 equal to 0, k2 equal to 0, and kn equal to 0. Since we have a non-zero solution, that's a contradiction, which means our assumption must be wrong. So v1 cannot be 0. This is a contradiction because k1 cannot be 1. k1 equal to 1 cannot be a solution. That's a contradiction. Once we find contradiction, that means our assumption was wrong. So v1 cannot be 0. If v1 is not a 0 vector, since S contains only one vector, and this vector is not 0, then by the definition here, S is a linearly independent set. Case 2. S contains at least two vectors. So let S be the set of V1, V2 up to Vn. We try to prove that S is linearly independent. Again, prove by contradiction. Assume S is linearly dependent. Prove by contradiction. Assume S is linearly dependent. That means one of the vectors in S can be written as a linear combination of the others. Then there exists Vi in S. Such that Vi can be written as a linear combination of the other vectors. Such that Vi equal to C1 times V1 plus C2 times V2 plus Ci minus 1 times Vi minus 1. Vi is here, so I skip Vi. Next term is Ci plus 1, Vi plus 1. And the last term is Cn, Vn. If S is linearly dependent, then one of the vector can be written as a linear combination of the other vectors. Next, this equation, I can rewrite this equation by moving Vi to the right side. If I move Vi to the right side, I get 0 equal to C1 V1 plus C2 V2 plus Ci minus 1 Vi minus 1 plus Vi plus Ci plus 1, sorry, minus Vi. If I move Vi over, I get minus Vi here. Plus the last term is Cn, Vn. Then, if we compare this equation with this vector equation here, we can see that C1 equal to K1, C2 equal to K2, and Cn equal to Kn. That's one of the solutions to this equation. Hence, K1 equal to C1, K2 equal to C2, Ki minus 1 equal to Ci minus 1, Ki equal to negative 1, Ki plus 1 equal to Ci plus 1, Kn equal to Cn. Those are solutions to this vector solution, to this vector equation. Those are solutions to this vector equation. They are solutions to the vector equation. K1 V1 plus K2 V2 plus Kn Vn equal to 0. And they are not all zeros. At least Ki is not 0. They are not all zeros. At least Ki is not 0. Therefore, it's a contradiction. Since Ki is not 0, it's a contradiction. Once we find contradiction, that means assumption was wrong. So S cannot be linearly dependent. S must be linearly independent. Therefore, S must be linearly independent. Let's complete the proof of this theorem. So, a set S is linearly independent if and only if the only solution to this vector equation is k1 equals 0, k2 equals 0, and kn equals 0. Next, let's look at an example. Let v1, v2, v3 be vectors in R2. Determine whether they are linearly independent. So, how can we determine whether they are linearly independent? According to the previous theorem, a set S is linearly independent if and only if the only solution to the vector equation is k1 equals 0, k2 equals 0, and kn equals 0. So, in order to determine whether the vectors v1, v2, v3 they are linearly independent, we first of all set k1 v1 plus k2 v2 plus k3 v3 equals 0. Then, according to the previous theorem, if all k's are 0, then we can say v1, v2, v3 they are linearly independent vectors. So, how can we set out an equation and solve for k? Here, v1 is the vector 2, 3. v2 is the vector 1, -4. v3 is the vector 7, -6, equal to 0. This 0 in R2 is 0, 0. 0 vector in R2 is 0, 0. Then, on the left side, let me first of all distribute k1, k2, k3. I get 2k2, 2k1, 3k1, k2, -4k2, 7k3, -6k3, equal to 0, 0. Then add the vectors. When we add the vectors, add the corresponding components. I get 2k1 plus k2 plus 7k3. And the second component is 3k1 minus 4k2 minus 6k3 equal to 0, 0. Then matrix component. First component must be 0. Second component must also be 0. So I have the equations 2k1 plus k2 plus 7k3 equal to 0. 3k1 minus 4k2 minus 6k3 equal to 0. Then this is a system of linear equations. If I write it as an augmented matrix, I have 2, 1, 7, 0, 3, -4, -6, 0. So if you observe this augmented matrix, we can see that the first column is the same as v1. The second column is the same as v2. The third column is the same as v3. The last column is 0. So a quick way to set our vector function is put the first vector in the first column, put the second vector in the second column, put the third vector in the third column, and put a constant in the last column. That's a quick way to set our vector equation. So a quick way to set out a vector equation is I put v1 in the first column, put v2 in the second column, put v3 in the third column, and put 0 in the last column. Next, let's solve the equations for k1, k2, k3. Use Gauss-Jordan elimination. First step, try to make leading 1 in the first entry here. All I can do is I can multiply first row by -1, add it to the second row, I get 2, 1, 7, 0, 1, -5, -13, 0. Next, I can interchange row 1 and row 2. Interchange row 1 and row 2. I get 1, -5, -13, 0. 2, 1, 7, 0. Next, I multiply first row by -2, add it to the second row. So first row is 1, -5, -13, 0. Multiply first row by -2, add it to the second row, I get 0. 10 plus 1 is 11. 26 plus 7 is 33. Next, I can divide the second row by 11. Take 1 over 11 times second row. I get 0, 1, 3, 0 in the second row. Leave first row the same. Next, in the second row, try to find a leading one. It is a leading one here, so try to make the entries above leading one to be 0. I can multiply second row by 5, add it to the first row. So I get 1, 0, 2, 0. Leave second row the same, 0, 1, 3, 0. If we write a matrix back as equation, I have K1 plus 2K3 equal to 0. And second equation is K2 plus 3K3 equal to 0. Here, K3 is a free variable because there's no leading one here. K3 is a free variable. So for the solution of the system, let K3 be T. Then let me run the equation here. K1 is -2K3. K2 is -3K3. If I let K3 be T, then K1 is -2T. K2 is -3T. K3 is T, where T can be any real number. Since T can be any real number, for example, if I let T be 1, then K1 is -2, K3 is -3, K3 is 1. So there exists non-zero solution for case. If there exists non-zero solution for case, then this vector v1, v3, v1, v2, v3, they are linearly dependent. If there exists non-zero solutions for K1, K2, K3, then the vectors v1, v2, v3, they are linearly dependent. So v1, v2, v3, they are linearly dependent. They are linearly dependent vectors. Next example, let matrices A, B, and C be vectors in M22. Determine whether they are linearly independent. According to the previous theorem, if we try to determine whether these three vectors are linearly independent, we first of all set K1 times A plus K2 times B plus K3 times C equal to 0. If the only solution to this vector equation is K1 equal to 0, K2 equal to 0, and K3 equal to 0, then these three vectors A, B, and C, they are linearly independent. Otherwise, if there exist non-zero solutions, for K1, K2, K3, then these three vectors, they are linearly dependent. So let's solve this equation for K1, K2, and K3. for this vector equation, k1 times A plus k2 times D plus k3 times C. Matrix A is the matrix 1, 2, -2, -1. B is the matrix 0, 1, 2, 3. C is the matrix 2, 3, 1, 6. So k1 times A plus k2 times D plus k3 times C equal to 0. This 0 here is the zero vector in M22, which is the matrix 0, 0, 0, 0. This 0 here is the 0 vector in M22, which is 0, 0, 0, 0. Then solve this equation for k1, k2, k3. Here I can first of all distribute k1, k2, k3, since they are scalars. If I distribute k1, I get k1, 2k1, -2k1, -k1. If I distribute k2, I get 0, k2, 2k2, 3k2. If I distribute k3, I get 2k3, 3k3, k3, 6k3 equal to 0, 0, 0, 0. Next, add these matrices. For matrix addition, we add the corresponding entries. I get k1 plus 0 plus 2k3, 2k1 plus k2 plus 3k3, -2k1 plus 2k2 plus k3, and the last entry here is -k1 plus 2k2 plus 3k2 plus 6k3 equal to 0, 0, 0, 0. If two matrices equal to each other, that means their corresponding entries must be the same. So I have k1 plus 2k3 equal to 0. 2k1 plus k2 plus 3k3 equal to 0. -2k1 plus 2k2 plus k3 equal to 0. -k1 plus 3k2 plus 6k3 equal to 0. This is a system of linear equations. If I write it as an augmented matrix, I have 1, 0, 2, 0, 2, 1, 3, 0, -2, 2, 1, 0, -1, 3, 6, 0. That's an augmented matrix of this system of linear equations. Now, if we observe this matrix with the vectors A, B, and C, we can see that the entries of A, the entries in matrix A, the entries in matrix A is the first column, 1, 2, -2, -1. The entries in matrix B is the second column, 0, 1, 2, 3. The entries in matrix C, 2, 3, 1, 6 is the third column. And the entries of the 0 vector is 0, 0, 0, 0. So we can see that a quick way to set up a vector equation, is that we put the entries of the first matrix in the first column, put the entries of the second matrix in the second column, put the entries of the third matrix in the third column, and put the entries of the constant in the last column. That's a quick way to set up a vector equation. So a quick way to set up this vector equation is that put entries in matrix A in the first column. I get 1, 2, -2, -1. Put the entries in matrix B in the second column. I get 0, 1, 2, 3. Put the entries in matrix C in the third column. I get 2, 3, 1, 6. And put the entries in the 0 matrix in the last column. I get 0, 0, 0, 0. Then we can use Gauss-Jordan elimination to solve for K1, K2, K3. Let's use Gauss-Jordan elimination. First of all, in the first row, we have a leading one here. Next, try to make all entries below leading one to be 0. I can first of all multiply first row by -2, add it to the second row. I get 1, 0, 2, 0. 0, 1, -1, 0. Next, I can multiply first row by 2, add it to the third row. I get 0, 2, 5, 0. Next, I can directly add the first row to the third row. Add the first row to the fourth row. I get 0, 3, A, 0. Next, in the second row, we have a leading one here. Try to make all entries above or below leading one to be 0. So try to make 0 here, 0 here. So I can leave the first row the same. 1, 0, 2, 0. Leave the second row the same. 0, 1, -1, 0. Next, I can multiply second row by -2. Add it to the third row. I get 0, 0, 7, 0. Next, I can multiply second row by -3. Add it to the third row. Add it to the fourth row. I get 0, 0, 11, 0. Next, let's move to the third row. In the third row, in the third column, try to make leading one here. So I can divide the third row by 7. Take 1/7 times row 3. I get 1, 0, 2, 0. 0, 1, -1, 0. 0, 0, 1, 0. 0, 0, 11, 0. Next, that's a leading one in the third row. I try to make all entries above or below leading one to be 0. So here I can multiply third row by -2, add it to the first row. Multiply third row by -2, add it to the first row. I get 1, 0, 0, 0. Next, I can directly add the third row to the second row. I get 0, 1, 0, 0. Leave the third row the same. Next, I can multiply third row by -11, add it to the fourth row. I get 0, 0, 0, 0. So the only solution to this equation is K1 equal to 0, K2 equal to 0, K3 equal to 0. If the only solution to this vector equation is K1 equal to 0, K2 equal to 0, K3 equal to 0, then vectors A, B, and C, they are linearly independent. So A, B, and C are linearly independent vectors. So A, B, and C, they are linearly independent vectors, since the only solution for the scalars is 0, 0, 0. Next example, let functions f, g, h be vectors in P2. Here, P2 is the set of all polynomials with degree less or equal to 2. Determine whether they are linearly independent. According to the previous theorem, if we want to determine whether these three vectors are linearly independent, we first of all set k1 times function f plus k2 times function g plus k3 times function h equal to 0. If the only solution for this vector equation is k1 equals 0, k2 equals 0, and k3 equals 0, then the vectors f, g, h, they are linearly independent. Otherwise, if there exist non-zero solutions for k1, k2, or k3, then these three vectors f, g, h, they are linearly dependent. So let's solve this vector equation for k1, k2, k3. How can we solve it here? For this vector equation, k1 times f plus k2 times g plus k3 times h equal to 0. I can first of all distribute k1, k2, k3. I get k1 s squared minus 2k1x plus k2 s squared plus k2x plus 3k2 plus k3x squared plus 7k3x plus 9k3 equal to 0. Then combine like terms. Combine k1x squared, k2x squared, and k3x squared together. I get k1 plus k2 plus k3 s squared. Let's combine negative 2k1x, k2x, and 7k3x together. I get negative 2k1 plus k2 plus 7k3 equal to 0 times x. Next, combine the constant term together. I have 3k2 plus 9k3 . If a polynomial equal to 0, that means all its coefficients must be 0. If a polynomial equal to 0, that means all its coefficients must be 0. So I have k1 plus k2 plus k3 equal to 0. Negative 2k1 plus k2 plus 7k3 equal to 0. 3k2 plus 9k3 equal to 0. This is a system of linear equations. If we write it as augmented matrix, I have 1, 1, 1, 0. Negative 2, 1, 7, 0. 0, 3, 9, 0. That's the augmented matrix of this system of linear equations. Now, if we observe this matrix, we can see that the first column is the coefficient of the first function, 1, negative 2, 0. The second column is the coefficient of the second function, 1, 1, 3. The third column is the same as the coefficient of the third function, 1, 7, 9. And the last column is 0. So, a quicker way to set out this vector equation is that I put the coefficient of function f in the first column, s squared x 1. Put the coefficient of function f in the first column, 1, negative 2, 0. Put the coefficient of function g in the second column, I get 1, 1, 3. Put the coefficient of function h in the third column, I get 1, 7, 9. For zero polynomial, we can consider zero polynomial. 0 is 0x squared plus 0x plus 0. So the coefficient for the zero polynomial is 0, 0, 0. The coefficient of zero polynomial is 0, 0, 0. That's a quick way to set out augmented matrix. Next, use Gauss-Jordan elimination, solve an equation for K1, K2, K3. In the first row, we have a leading one already. So I try to make all entries below leading one to be 0. I can first of all multiply first row by -2. Multiply first row by 2, add it to the second row. Multiply first row by 2, add it to the second row. I get 1, 1, 1, 0 in the first row. 0, 3, 9, 0. 0, 3, 9, 0. Next, I can divide the second row by 3 and make leading one here. Take 1/3 times second row. I get 1, 1, 1, 0. 0, 1, 3, 0. 0, 3, 9, 0. Now this is the leading one. We try to make all entries above or below leading one to be 0. I can first of all multiply second row by -1, add it to the first row. I get 0, 1, 0, -2, 0. Second row stays the same. Next, I can multiply second row by -3, add it to the third row. I get 0, 0, 0. So, if I write this matrix back to equation, first row is K1 minus 2K3 equal to 0. Second row is K2 plus 3K3 equal to 0. In the third column here, there's no leading one. That means K3 is a free variable. So, write K1, K2 in terms of K3. I get K1 equal to 2K3. K2 equal to -3K3. K3 is a free variable. So I can let K3 equal to T. Then K1 equal to 2T. K2 equal to -3T. And K3 equal to T, where T can be any real number. So since T can be any real number, there exist non-zero solutions for K1, K2, K3. Since T can be any real numbers, that means there exist non-zero solutions for K1, K2, K3, which means the vectors f, g, h, they are linearly dependent. If there exist non-zero solutions for K1, K2, K3, the vectors f, g, h, they are linearly dependent. So f of x, g of x, f, g, h, they are linearly dependent vectors. Next example, let V1, V2, V3 be vectors in R3. Part A, determine whether they are linearly independent. Part B, determine whether they span R3. So let's do part A first. In order to determine whether these three vectors are linearly independent, I first of all set K1 V1 plus K2 V2 plus K3 V3 equals 0. Then, for the augmented matrix of this vector equation, I write the component of V1 in the first column, component of V2 in the second column, component of V3 in the third column, and the component of 0 vector in the last column. 0 vector in R3 is 0, 0, 0. Then we can use Gauss shorter elimination to solve the equations for K1, K2, K3, and then based on K1, K2, K3, we can determine whether V1, V2, V3 they are independent or not. Here I'll show you a different way. Instead of solving the equation, I'll show you a different way to determine whether V1, V2, V3 they are linearly independent. Now, this augmented matrix it can be rewritten as a matrix equation, AS equal to 0. This augmented matrix can be rewritten as a matrix equation, AS equal to 0. Where A is the matrix 1, 2, 3, 0, 1, 2, 3, negative 4, negative 1. And X is the variables, it's the unknowns. K1, K2, K3. X is the unknowns. K1, K2, K3. And 0 is the column vector, 0, 0, 0. 0 is the column vector, 0, 0, 0. Note, since A is a square matrix, since A is a square matrix, then by the equivalent statements, since A is a square matrix, then by the equivalent statements, if determinant of A is not 0, if determinant of A is not 0, then the homogeneous system A is equal to 0 has only trivial solutions. The homogeneous system A is equal to 0 has only the trivial solutions. So K1 equal to 0, K2 equal to 0, and K3 equal to 0. If the only solution is K1 equal to 0, K2 equal to 0, K3 equal to 0, then the vectors V1, V2, V3, they are linearly independent. However, if determinant of A is 0, then by equivalent statements, the homogeneous system AS equal to 0 has non-trivial solutions. If it has non-trivial solutions, that means at least one of K1, K2, K3 is not 0. At least one of K1, K2, K3 is not 0. So if determinant of A is 0, then AS equal to 0 has non-trivial solutions. That means at least one of K1, K2, K3 is not 0. If at least one of K1, K2, K3 is not 0, that means the vectors V1, V2, V3, they are dependent. Let me put it here. Hence V1, V2, V3 are linearly dependent. So if determinant of A is not 0, then AS equal to 0 has only the trivial solution, which means K1 is 0, K2 is 0, K3 is 0. Then by the previous theorem, we know that V1, V2, V3 must be linearly independent. Otherwise, if determinant of A is 0, then by equivalent statements, AS equal to 0 has non-trivial solutions. That means at least one of K1, K2, K3 is not 0. Hence, by the previous theorem, we know that V1, V2, V3, they are linearly dependent vectors. So keep this note in mind. So when A is a square matrix, we can determine whether the vectors are linearly independent by taking determinant. Now here, take determinant for matrix A. Take determinant for matrix A. Let me copy matrix A, put it here, and put it here. Matrix A here is 1, 2, 3, 0, 1, 2, 3, -4, -1. Take determinant for matrix A. We can take determinant along any row or any column. Here in the first column, since there's a 0, I take determinant along the first column. So I get 1 times determinant of the submatrix 1, 2, -4, -1 minus 0 plus 3 times determinant of the submatrix 2, 3, 1, 2. Then take determinant. 1 times -1 is -1. -4 times 2 is -8. Minus -8 is plus 8. Plus 3 times 2 times 2 is 4. 1 times 3 is 3. I get -1 times 7 plus 3 times 1. That's -7 plus 3. That's -4. Since determinant of A is not 0, we know that vectors V1, V2, V3, they are linearly independent. Here should be linearly independent vectors. They are linearly independent vectors. Now, for part B, determine whether they span R3. So, in order to determine whether they span R3, we try to determine whether we can write every vector in R3 as a linear combination of v1, v2, v3. So let's first of all pick arbitrary vector in R3. Let B equal to b1, b2, b3. Let B be an arbitrary vector in R3. Then we set k1 v1 plus k2 v2 plus k3 v3 equal to B. If there exist solutions for k1, k2, k3, that means the vectors v1, v2, v3 span R3. Otherwise, if there's no solutions for k1, k2, k3, then the vectors v1, v2, v3, they don't span R3. So for this vector equation, for its augmented matrix, I can put a component of v1 in the first column, component of v2 in the second column, component of v3 in the third column, component of B in the last column. Component of B is B1, B2, B3. Then again, this augmented matrix can be rewritten as a matrix equation AS equal to B. Where A is the matrix 1, 2, 3, 0, 1, 2, 3, negative 4, negative 1. X is the unknowns K1, K2, K3. And B is the column vector B1, B2, B3. Note, since here A is a square matrix, then by equivalent statements, if determinant of A is not 0, then the linear system AS equal to B is consistent. By equivalent statement, if determinant of A is not 0, then the linear system AS equal to B is consistent. Consistent means there exist solutions for X, which means there exist solutions for K1, K2, K3. So there exist solutions for K1, K2, K3. If there exist solutions for K1, K2, K3, that means I can write every vector in R3 as a linear combination of V1, V2, V3. Hence, V1, V2, V3 span R3. On the other hand, if determinant of A is 0, then by the equivalent statements, the linear system AX equal to B is inconsistent. Inconsistent means there's no solutions for K1, K2, K3. So there does not exist solutions for K1, K2, K3. If there's no solutions for K1, K2, K3, that means we cannot write arbitrary vector in R3 as a linear combination of V1, V2, V3. Hence, V1, V2, V3, they don't span R3. Hence, V1, V2, V3, they don't span R3. So let's take determinant. Take determinant for matrix A. According to part A, we know that determinant of A is not 0. According to part A, we know that determinant of A is negative 4. This matrix A and this matrix A and this matrix A, they are exactly the same matrix. According to part A, we know that determinant of A is negative 4, which is not 0. Hence, V1, V2, V3 span R3. If determinant of A is not 0, the vectors V1, V2, V3 span R3. So keep this rule in mind. Keep this rule in mind. And in general, let V1, V2, Vn be vectors in a vector space V. Let A be the matrix with V1, V2, and Vn as column vectors. Let A be the matrix with V1, V2, Vn as column vectors. If A is a square matrix, we can apply equivalent statements. Then take determinant for A. By equivalent statements, if determinant of A is not 0, then V1, V2, Vn, they are linearly independent. If determinant of A is not 0, then the vectors are linearly independent. And also, if determinant of A is not 0, the vectors v1, v2, v3, the vectors v1 to vn span the vector space V. If determinant of A is not 0, then by the equivalent statements, v1, v2, vn, they are linearly independent vectors, and they span V, they span a vector space V. However, if determinant of A is 0, then v1, v2, vn, they are linearly dependent. If determinant A is 0, then the vectors v1, v2, vn, they are linearly dependent. If determinant of A is 0, the vectors, they are linearly dependent. And also, they don't span the vector space. And v1, v2, vn, they don't span the vector space V. So keep this idea in mind. If A is a square matrix, take determinant. If determinant is not 0, then they are independent vectors and they span the vector space. If determinant of A is 0, then they are linearly dependent and they don't span the vector space. However, if A is not a square matrix, we cannot apply equivalent statements. Then we must use Gauss-Jordan elimination to reduce the matrices. If A is not a square matrix, then there's no shortcut. We must use Gauss-Jordan elimination to reduce the matrices. There's no shortcut. If A is not a square matrix, we must use Gauss-Jordan elimination to reduce the matrices. There's no shortcut. And in the previous examples, for example, example 3, the matrix in front of constant is a square matrix. So here I can take determinant for this matrix. Then use determinant to determine whether the vectors f, g, h, they are linearly independent or not. However, in example 2, the matrix in front of a constant is not a square matrix. That means we cannot find a determinant. So there's no shortcut. We must use Gauss-Jordan elimination to reduce the matrix. There's no shortcut. And in example 1, again, the matrix in front of a constant is not a square matrix. That means we cannot take determinant. We must use Gauss-Jordan elimination to reduce the matrices. So keep this rule in mind. This rule only works when A is a square matrix. Otherwise, we must use Gauss-Jordan elimination. Next example. In example 1 and 3, the vectors are linearly dependent. We know that if the set of vectors are linearly dependent, then we can write one vector as a linear combination of the other vectors. So, in example 1 and 3, write one of the vectors as a linear combination of the others. Write one of the vectors as a linear combination of the others. So, in example 1, the solutions for K1, K2, K3 the solutions for K1, K2, K3 are K1 equal to negative 2t, K2 equal to negative 3t, K3 equal to t. T can be any real number. Since t can be any real number, let's pick a number for t. Make it simple. Let's pick t equal to 1. let t equal to 1, then k1 equal to -2, k2 equal to -3, and k3 equal to 1, which means this is a solution to the vector equation. This is a solution to the vector equation k1 v1 plus k2 v2 plus k3 v3 equals 0. So k1 v1 plus k2 v2 plus k3 v3 equal to 0. I can isolate one of the vectors here. Let me get v3 by itself because the coefficient is the simplest. Let me get v3 by itself. v3 can be rewritten as 2v1 plus 3v2. So I write one vector as a linear combination of the others. We can check the answer. v1 is, in example 1, v1 is 2, 3, v2 is 1, 4, v3 is 7, -6. We can check the answer. 2 times v1, v1 is 2, 3, plus 3 times v2, v2 is 1, -4. Distribute 2, I get 4, 6. Distribute 3, I get 3, -12. Adding up, I get 7, -6, which is v3. So 2 times v1 plus 3 times v2 equal to v3. In example 3, the solutions for k1, k2, k3 in example 3, the solution for k1, k2, k3 are k1 equal to 2t, k2 equal to -3t, k3 equal to t. T can be any real number. k1 equal to 2t, k2 equal to -3t, k3 equal to t, where t can be any real number. So let's find a non-zero solution for k1, k2, k3. Make it simple. Let's pick 1. Let t equal to 1. If I let t equal to 1, then k1 equal to 2, k2 equal to -3, k3 equal to 1. Then this is a solution of the vector equation k1 times f plus k2 times g plus k3 times h equal to 0. That means k1, k2, k3 satisfies this equation. So 2 times f of x minus 3 times g of x plus 1 times h of x equal to 0. Then solve the equation for one of the vectors. In general, make it simple. Let me solve the equation for h of x. H of x can be rewritten as -2f of x plus 3g of x. So here I write one vector as a linear combination of the other two vectors. We can check the answer. Let's check. Function f is s squared minus 2x. Function g is s squared plus x plus 3. If we multiply, we get -2s squared plus 4x plus 3x squared plus 3x plus 9. If we combine like terms, we get s squared plus 7x plus 9. S squared plus 7x plus 9. That's exactly the same as function h. So here I write h as a linear combination of f and g. Next, let me introduce plus or minus theorem. Let S with vectors v1, v2, vn be a non-empty subset of a vector space V. Part A. Let U be a vector in V, and U doesn't belong to S. If S is linearly independent, and U cannot be written as a linear combination of other vectors in S, then S union U is still a linearly independent set. S union U means I add U to S. If S is linearly independent, and U cannot be written as a linear combination of vectors in S, then when I add U to S, the new set is still a linear independent set. That's called plus theorem. Part B. Let U be a vector in S. If U can be written as a linear combination of other vectors in S, then span of S is the same as span of S minus U. So part B says, if U can be written as a linear combination of other vectors in S, then if I remove U from S, set S, the set still spans the same space as S. If I remove U from S, the set still spans the same space as S. This is called minus theorem. Now let's prove it. Let's prove part A first. Let U be a vector in V, and U doesn't belong to S. If S is linearly independent, and U cannot be written as a linear combination of vectors in S, then we try to prove that S union U is still a linearly independent set. So we try to prove S union U is still a linear independent set. S union U means I add U into set S. That's the set of vectors v1, v2, vn, and U. So this set contains v1, v2, vn, and U. We try to prove this set is linearly independent. So I first of all set k1 v1 plus k2 v2 plus kn vn plus kn plus 1 times vector U equal to 0. I first of all set k1 v1 k2 v2 plus kn vn plus kn plus 1 times U equal to 0. We try to prove that all k1, k2, kn, they are all zeros. If I prove that all k's are zeros, that means this set v1, v2, vn, and U, they are linearly independent. How can we prove all k's are zero? Let's first of all prove by contradiction. Assume k sub n plus 1 is not 0. We try to show that that's impossible. Assume k sub n plus 1 is not 0. Then I can move every term to the right side. I get k plus 1 times U equal to k1 v1 plus, if I move over, the sign change. I get negative k1 v1 minus k2 v2 minus kn vn. Since k sub n plus 1 is not 0, I can divide both sides by k sub n plus 1. So U can be written as negative k1 over kn plus 1 times v1 minus k2 over kn plus 1 times v2 minus kn over kn plus 1 times vn. Then here I write U as a linear combination of v1, v2, vn, which is impossible because, according to assumption, U cannot be written as a linear combination of vectors in S. That's impossible. it's a contradiction. Once we found contradiction, that means our assumption was wrong. So Kn plus 1 must be 0. If Kn plus 1 is 0, then this equation can be rewritten as K1 V1 plus K2 V2 plus Kn Vn plus 0 equal to 0. If Kn plus 1 is 0, 0 times U is 0. I got 0 here. That's the same as K1 V1 plus K2 V2 plus Kn Vn equal to 0. Since S is linear independent set, if I have K1 V1, K2 V2, Kn Vn equal to 0, then K1 must be 0, K2 must be 0, and Kn must be 0. Since S equal to V1, V2, Vn is linear independent, then the only solution to this equation is K1 equals 0, K2 equals 0, and Kn equals 0. Then we have K1 equals 0, K2 equals 0, and Kn equals 0. Since K1 is 0, K2 is 0, Kn is 0, and Kn plus 1 is also 0, then these vectors, including U, must be linearly independent. Since in this equation, K1 is 0, K2 is 0, Kn is 0, and Kn plus 1 is also 0, then the vectors V1, V2, Vn, including U, are linearly independent. Hence, S union U is linearly independent. Let's complete the proof for part A. So, if S is a linear independent set, and U cannot be written as a linear combination of vectors in S, then S union U, if I add U to S, is still a linear independent set. That's part A. Part B. Let U be a vector in S. If U can be written as a linear combination of other vectors in S, then if I remove U, the span of the set S minus U is the same as the span of the set S. So in part B, we try to show that these two sets equal to each other. In order to show two sets equal to each other, we must show that they are subsets of each other. We must show left side is a subset of right side, and right side is a subset of left side. For part B, since U belongs to set S, then U equal to Vi for some I equal to 1, 2, 3, or n. Since S has vectors V1, V2 up to Vn, and U is one of these vectors, so U equal to Vi for I equal to 1, 2, 3, or n. U is one of the vectors, one of the Vi. Let's first of all show that left side is a subset of right side. let W belong to span of S. Then W can be noted as a linear combination of all vectors in S. So W equal to K1 V1 plus K2 V2 plus Ki minus 1 Vi minus 1 plus Ki Vi plus Ki plus 1 Vi plus 1 plus the last element Kn Vn. If W belongs to span of S, then W can be noted as a linear combination of all vectors in S. Vector in S is V1, V2 up to Vn. R is somewhere in the middle. Now, since U can be noted as a linear combination of other vectors in S, then U can be noted as Vi equal to U can be noted as C1 times V1 plus C2 times V2 plus Ci minus 1 times Vi minus 1. Vi is here, so skip Vi. Next term is Ci plus 1, Vi plus 1, plus Cn Vn. So Vi can be written as a combination of other vectors. Next, plugging Vi here. Plugging Vi into this equation. Then W can be noted as K1 V1 plus K2 V2 plus Ki minus 1 Vi minus 1 plus, let me put K times Vi in the next row, plus Ki times C1 V1 plus C2 V2 plus Ci minus 1 Vi minus 1 plus Ci plus 1 Vi plus 1 plus Cn Vn plus Kn Vn. I plug in Vi into this equation. That's what I get here. Next, distribute Ki. I get K1 V1 plus K2 V2 plus Ki minus 1 Vi minus 1 plus, here, distribute Ki. I get Ki C1 times V1, Ki C2 times V2, Ki Ci minus 1 times Vi minus 1, Ki Vi plus 1, Ki Ci plus 1 times Vi plus 1. plus plus Ki Cn times Vn. That's this row. Continue, plus the next row, Kn, the next row here, I forget, Ki plus 1, Vi plus 1, plus Kn, Vn. Here, after I substitute, I still have Ki plus 1, Vi plus 1. I substitute Vi here. Next term is K sub I plus 1, V sub I plus 1. Last term is Kn, Vn. Next, let's combine like terms. Combine like terms. For V1, I have K1 V1 plus Ki Ci V1. So for V1, I have K1 plus Ki C1 V1. Combine like terms. For V2, I have K2 plus Ki C2 V2. Continue. For Ki minus 1, for Vi minus 1, I have K sub I minus 1 plus Ki times C sub I minus 1 times Vi minus 1. Next term will be Ki plus 1. For Ki plus 1, for Vi plus 1, the coefficient here is Ki plus 1, Ki Ci plus 1. Times V sub I plus 1 plus, then the last term is, let me put the last term here. For Vn, the coefficient here is Kn and Ki Cn. Times Vn. Those are scalars. Those are scalars. So W can be written as a linear combination of all vectors in S take with U. Here, W is a linear combination of V1, V2, Vi minus 1, Vi plus 1 up to Vn. Here I skip Vi, and Vi is U. So W is a linear combination of all vectors except U, which means W can be written as a linear combination of all vectors in S minus U. Hence, W belongs to the span of S minus U. If all elements in span of S belong to span of S minus U, that means span S is a subset of span of S minus U. Therefore, span of S is a subset of span of S minus U. That's one deduction. I show that left side is a subset of right side. Next, I try to show that right side is a subset of left side. Next, I try to show that right side is a subset of left side. Next, let W belong to span of S minus U. This W and this W, they are not the same thing. This W and this W, they are not the same thing. Here, let W be a vector in span of S minus U. Then, W can be written as a linear combination of all vectors in S except U. U is Vi. So W can be written as a linear combination of all vectors in S except Vi. So W equal to K1 V1 plus K2 V2 plus Ki minus 1 times Vi minus 1. Then skip V. Next is Ki plus 1 Vi plus 1 plus Kn Vn. Then W can be rewritten as K1 V1 plus K2 V2 plus Ki minus 1 Vi minus 1. I try to add Vi here. So if there's no Vi, I can write plus 0 times Vi. If there's no Vi, I can write plus 0 times Vi plus K sub I plus 1 Vi plus 1 plus Kn Vn. So W is a linear combination of V1, V2 up to Vi plus 1 and Vn. Therefore, W is a linear combination of all vectors in S. So W can be written as a linear combination of all vectors in S. Hence, W belongs to span of S. So here I show that all elements in span of S minus U belong to span of S. Therefore, span of S minus U is a subset of span of S. Since two sets are subsets of each other, then they must be the same. Therefore, span of S equal to span of S minus U. That's the proof of the minus theorem. So minus theorem says in a dependent set, if we remove a vector that can be written as a linear combination of the other vectors, the spanning of the set stays the same. The span of the set stays the same. That's the minus theorem. This is a plus theorem. That's the minus theorem.